Now, let us discuss what are the applications of graph. As we discussed different implementation methods of graph, that that is breadth first search, then depth first search, and many more techniques that we discussed as before in this slide. Now it is a time when we have to discuss what is the application of a graph, in which area we can actually implement this graph so that we can use it in a efficient manner. So topological sorting is one of the option in that we can use the graph techniques, the DAG, that is the directed acyclic graph, efficiently in various applications. Now, what is topological sorting? Topological sort of a directed acyclic graph, that is DAG, is defined as a linear ordering of its nodes. Now, linear ordering of its nodes means what? See here, this is a graph, and we are providing some topological sort of the graph, that in what are the different types of linear ordering of the graph. Suppose we are moving from A to B, B to again B to C, then C to D and E. Or we can use the path as A, C, B, then D and E, and many more. So there are various topological sorting are available over here, which defined as a linear ordering of its nodes, in which each node comes before all nodes to which it has outbound edges. Outbound edges. Okay, so a topological sort of a directed acyclic graph. Now there is no cycle present. Directed acyclic. No cycle is there. Means what is the meaning of cycle? That we know that if the one vertex A is moving to the vertex B, and again vertex B is moving to the vertex C, and again vertex C is moving to the vertex A, if such a type of a loop is created, if such type of a loop is created, then it is called as cyclic graph. If the loop is not created, then it is called as directed acyclic graph. So, as these are the two DAGs available in front of you, there is no cycle present over in this graph. So, if the cycle is present, then we cannot apply the topological sorting on that particular graph. So, a topological sort of a DAG G is an ordering of the vertices of a graph such that if U if G contains an edge, that is U to V, U comma V, then U appears before V in the ordering. U should appears before V in the ordering. Note that topological sort is possible only on directed acyclic graph. So this is very important, that this is applied only on directed acyclic graph that do not have any cycle. That do not have any cycle. Okay, so it is applied on a graph, and the U comes before V. U appears before V. So we have to calculate in that case the integrity of each and every node, so that we can understand that U comes before V all the time, and there should not be any cycle present in that particular form. So these are the important concept of topological sorting, and the graph, it should be DAG, that is directed acyclic graph of linear ordering. Now, topological sorting is used in various areas like scheduling applications, jobs or a task, you can use this topological sorting. So topological sorting is used in this particular areas. So these are the various, these are the two topological sort is there in front of you to give just idea of what is topological sort or how in which manner the graphs are looks in this case of a topological sort. So graph are looking without any type of a loop, without any type of a cycle. Okay, and the second important thing is that u comes before v, and the second one is there is no cycle and u comes before v. So these are the two important points which are apply on topological sorting, and we can sort the element by using this technique. Here in front of you I am consider one example. With the help of that you can understand that what is topological sort. And again one more thing you can do, that with the help of such a type of a problem you can solve it systematically, so that you can apply this technique in the various areas like scheduling the job, scheduling the applications, jobs and tasks. So you can use this applications in that areas also. So consider a directed acyclic graph given in a figure. Find a topological sort T of a graph. The steps are given below. So this is the graph, and for this graph with the adjacency list we can calculate a topological sort, or we can find the what is the topological sort of this graph. So for that we have come across different steps. So with the help of the steps, step by step you can understand how we solve this particular problem. So step 1. In the step 1, find the in-degree of every node. So now what is in-degree of node? In-degree of a node means the number of edges coming to that node. Number of edges coming to that node. It is nothing but the in-degree of that node. So at the first step we calculate in-degree of all the nodes that are present in this graph, that is from A to F. So in-degree of A is 0 because there is no incoming edge to this A. Now in-degree of B is 1 edge. Now in-degree of C is 1. Why? 1 edge. In-degree of D. Now it is 2 because one edge is coming from B, another edge is coming from G. Now in-degree of E is 3. Now there are 3 edges are coming to the vertex E. Now in-degree of F is 1 and in-degree of G is 0 because there is no edge coming to the vertex G. So there are two such a type of vertex we have, in that there is no edge coming to the particular vertex. Okay, so for that, to explain this systematically we can take a help of the queue. So first of all, what is the second step? In a second step we enqueue all the nodes with a 0 in degree. We enqueue. Enqueue means we are inserting the queue those having in degree 0. Okay, and for that we are using front and the rear. So here front is equal to 1 and rear is equal to 2. And see, we are inserting in a queue the vertex which are having in degree 0. So these two vertex having in degree 0, that is A and G. Now in the step 3 we remove the front element A. Okay, because as it is having in degree 0, there is no edge coming to this vertex, so we are removing this element. As the functionality of this element is over, so we are remove the front element from the queue by setting front is equal to front plus 1, so that it can point to the next element, right? So front is equal to 2 rear is equal to 2 and q is having this 2, that is a and g. Now the next is set. In the step 4, what we are doing in a step 4, we find out that the in degree of b, so in degree of b is 1 as it is connected to the a, but we are removing a from the q, right? So there is no h to this b, now it is cut down, right? So initially the in degree of b is 1. Now this edge which is connected by a, it is cut down. So now the in degree of b is 0 because this edge is minimizes. So 1 minus 1 is 0. So there is no edge now. As a is removed from the cube, functionality of a is over. So that's why we write over here that in degree of b is equal to in degree of b minus 1. Okay. So there is no any vertex. Okay, so there is no any edge. So since B is the neighbor of A and A is removed from the Q, note that in degree of B is 0. Now the in degree of B is what? 0, because in degree of B initially is 1. So 1 minus 1 is 0. So add it on the Q. Okay, now the Q becomes front is equal to 2. Now front is incremented by 1, so front is equal to 2, rear is equal to 3. Why? Because now in the Q the element the b element is also having in degree 0. So the element which is having in degree 0 created the Q for that, and we are removing also the element from the Q. So now we are deleting the edge from A to B, right? Now the graph now becomes as shown in the figure. So there is no edge from A to B and there is no edge previously also from A to G. So there is no remove. So there is this edge only is removed. Remove the front element P from the Q by setting front is equal to front plus 1. So front also incremented again. So now front is equal to 2, rear is equal to 3. Now rear consists of 3 elements, that is A, G and P. Now in the step 6, what we are doing? We are focusing on the in degree of a D. In degree of a D is 2 initially, right? So yes, now since D is the neighbor of G and G is not having any incoming edge, it is having in degree 0. Okay, so if we are removing G from here, so the in degree of D is also minus 1 because initially the in degree of D is 2. Initially the in degree of D is equal to 2, right? So initially the in degree of D is 2, right? Now as we cutting this G as it is having in degree 0, so this edge is cutted and now the in degree of D is 1, but it is after the procedure. So in degree of D is equal to in degree of D minus 1. So now the in degree of D is equal to 1. Yes, so in degree of C is equal to 1, D is equal to 1, E is equal to 3. We know that 3 edges are coming to E. So in degree of E is 3. Now in degree of F is 1. Only one edge coming. So in degree of F is 1. Delete the edge from G to D. The graph now becomes as shown in the figure. So we are cutting this edge also. Okay, it is having in degree 0. We are cutting this edge. Now what will happen? Now in the step 7, remove the front element B. Sorry, remove the front element B from the Q by setting front is equal to front plus 1, so that front is equal to 4 and rear is equal to 3. Now it consists of 3 element which is having in degree 0. Yes. So in degree of C is equal to in degree of C minus 1 again. And in degree of D is also in degree of D minus 1. And in degree of E is also in degree of E minus 1, as these all are connected to B. Right? So since C, D, E are the neighbors of B and we are trying to delete the B. So now in degree of C is 0, 1 minus 1 0, D 2 minus 1 is 1 and E is 2, 3 minus 1 is 2. Okay, as we are deleting B from the Q. So since in degree of C and D is 0. C and D is 0. Now initially D is 1. D is 1 because of this edge. Now you are removing B, so now D becomes 0. Okay, at the first place D is 2. After removing G it is 1. After removing B is 0. So both are 0. Okay, so we are adding to the queue C and D because they are also having in degree 0. Okay, and we are incrementing the front again. Okay, so the graph becomes looks like this because we are in the previous slide also we are removing the degrees, removing the edges which are connected to the this B as it is having in degree 0. The vertex which is having in degree 0 we try to minimize, try to cut the edges which are connected to that particular vertex. Now remove the front element C from the cube by setting front is equal to front plus 1, and so front is equal to 5, rear is equal to 5. Now it is the time to do the next step on C as C is having in degree 0, right? So we are trying to delete the edge which is connected by C to other vertex. So set in degree of E is equal to in degree of E minus 1. Why? Because we are trying to cut this edge. So 1 minus 1 is 0. Initially the degree of E is 2. So 2 minus 1 is 1 now because we try to cut this edge also. Okay. So in degree of E is 1. Now the graph becomes like this. Right? A, B, G, C are and D are now inserted to the queue as they are having in degree 0. Okay, now it is time to work on E and F. Now in the step number 12 what we are doing, we are removing the front element D from the queue because it is having in degree 0, right, initially. So by setting again front is equal to front plus 1, now front is equal to 6, rear is equal to 5 because it is having 5 elements in the rear. Now in degree of E is equal to in degree of E minus 1. Edge is there. Cutted the edge because this is having in degree 0. Now the in degree of E is 0. Now we are again adding E to the Q. Okay. So now Q becomes A, G, B, C, D, E. So delete the edge between D and E. Now the graph becomes as shown in the figure. So there is only one edge left, that is E to F. Okay, so now there is, sorry, now again, yes, now here also as the in degree of E is 0, right, so we are again cutting this edge, so that is also ultimately into the Q, right? So we are doing this for remaining part also. So now what is the last step? So there is no edge, there is the 8 minute. So there is no edge in the graph and all the nodes have been added to the queue. So the topological sort of a T of a G can be A, G, B, C, D, E, F. When we arrange this node in a sequence, we find that if there is an edge from U to V, U appears before V. U appears before V. So if we are finding out, you can find that two things. That first is there is no any kind of a cycle, and second thing you can find that the U comes before V. U comes before V. U comes before V. So you can find out this part also in this graph, so that you can successfully sort the previous graph that we see in the first slide of the topological sorting, that is this one. It's a sort in this particular manner, okay? So there is no any cycle over here, right? and there is the vertex in which we find that there is an edge from U to V. Thank you.